Alright, so in this video we're going to do a couple examples, or a few examples rather, of sequences and limits of sequences. So let's start with one, for example, saying something like n to the 1 over n is going to be our an. Let's try to figure out whether this one converges or diverges. Well, this one, you have an exponent that depends on n, and the base depends on n. So this looks like something that you would do with a natural log, and write this as a natural log of n to the 1 over n. Kind of funny to write natural log of n, and that will give you a 1 over n natural log of n. So this gives you a natural log of n over n. Now, if you're going to compute this limit as n goes to infinity, natural log as n goes to infinity of n goes to infinity. So this goes to infinity. I don't know what I did there. This goes to infinity. And as n goes to infinity, this also goes to infinity. So we're talking about an indeterminate form of the form infinity over infinity. Now, since we have infinity over infinity, we are allowed to do L'Hopital's rule. So in this case, then we have that this is going to be, well, I'll need a limit first before we even do that. So let's say limit as n goes to infinity of an is going to be of the natural log of an is going to be the same as the limit as n goes to infinity of natural log of n over n, which now by L'Hopital's rule is going to be the limit as n goes to infinity of taking the derivative of the numerator. Derivative of natural log of n is 1 over n. I'm thinking of natural log as a real valued function, continuous real valued function, so I'm taking derivative in that sense. It's differentiable. Then the same here. It's kind of funny because an is a discrete quantity, but we're using the theorem that allows us to make it equal to a continuous function or a real valued function that we can then take derivatives of and do limits. So in that sense, then, this limit as n goes to infinity gives me a 0. From where the natural log of the limit, so if you exchange orders by the continuity of the natural log, you have that the natural log of an is equal to 0. That tells you that the limit as n goes to infinity, not natural log, limit as n goes to infinity of an, that infinity was terrible, try again, an is going to be 1 by exponentiating both sides. So from that, then, we see that this limit does exist, so we can say that then this converges. All right, let's do an example of one that possibly could diverge. So let me look for an example. All right, so let's look at this one, for example. So we would look at the limit as n goes to infinity of an. Since we have a function that defines it, we can do the limit as n goes to infinity of the cosine of the square root of n. And this one right here is going to be one of those that will oscillate because the cosine continues to oscillate. So as n goes to infinity, this is going to continue to oscillate. And so this one, actually, the limit will be undefined. It's not that it goes to infinity, it just keeps oscillating. So this is going to be undefined. And since our theorem, what we were requiring, remember, was that the limit be a number. And if that was the case, if this would have happened to be a number, then we could have said that that was the limit of our sequence. Well, in this case, we don't have that the limit is a number. Therefore, this sequence will diverge. All right, so in this case, we say that the sequence an, or in fact, let's just write the cosine of the square root of n, as n goes from 1 to infinity, diverges because it oscillates. Things can also go out to infinity as well. That's another possibility. Let's take a look at an example like that. So let's see, for example, an being the natural log of 1 over n, for example. So with that one, we would look at the limit as n goes to infinity of an is going to be equal to the limit as n goes to positive infinity of the natural log of 1 over n. And this one right here, you have to analyze what happens as n goes to infinity of 1 over n. This term tends to go to 0, and then what will happen is you have right continuity for the limit, so we can move the limit in and out. Sorry, for the natural log, so we can move the limit in and out, and we'll end up that this is going to be the limit as n goes to infinity. This would go to 0. The natural log at 0 is undefined. The limit from the right is negative infinity, so this whole thing would end up being negative infinity. So that's going to be that. By the way, as n goes to infinity, 1 over n approaches 0, but from the right. So that's why this limit is in fact defined, and it happens to be, well, defined to be negative infinity, I suppose. So in this case, for us, what matters is that the sequence then it diverges. So an as n equals 1 to infinity diverges. Now let's do one more. Let me add one page here real quick. So let's use the following. So we're going to use, for this one, we're going to use the squeeze theorem. So let's do something like the cosine of n over n, for example, as n goes to infinity. And we're going to be doing the squeeze theorem. So if you think about what happens as n goes to infinity, this term here is going to be going to 0. But this one remains to oscillate. So what I will do is I'll say that since the cosine of n will always be between 1 and negative 1, then if I divide by n, this expression, which is an, is going to be in between these two sequences. Now what I'm going to notice is that as n goes to infinity, 1 over n goes to 0, and also negative 1 over n goes to 0. So you see, I'm bounding this expression, or I'm sandwiching this expression between two quantities that are going down to 0. And that's basically going to be the idea of the squeeze theorem, or just monotonicity of the limit. This is what the theorem would say. So let an, I guess sequences everybody. So an, n equals 1 to infinity, bn, n equals 1 to infinity, and cn, be sequences, real value sequences. If no period there, if an less or equal than bn less or equal than cn for all n's between 1 and infinity, so all n natural, then the limits preserve that monotonicity. Really, I just would need 1 inequality. I don't need 3, but it just looks a lot more like what I have up there. But 2 suffice, actually, because you just apply it 2 times, you have 2 inequalities. But nonetheless, in this case, we have that. And so with that theorem, I apply it in the expression above, and I say that This is continuation of my problem. The theorem ends here. What I have is taking the limit of my an, which was the cosine of n over n, that is implied by my by the theorem, and then this gives us that 0 is less or equal than limit as n goes to infinity of an, which at the same time is less or equal than 0. Since I have that the quantity is greater or equal than 0 and also less or equal than 0, it better be that that quantity itself is equal to 0. And for that reason, this sequence an, that was given, if you will, by cosine of n over n, from n equals 1 to infinity, converges to 0. As n goes to infinity. All right, so that's going to be the type of problems we're going to be looking at this, looking at in this section. So you're often going to be using L'Hopital's. You're often going to be using your rational functions, or the properties for limits for rational functions. And so if you don't remember those, please brush up on those because you will definitely need them. Well, that will finish this section, and I'm gonna then start with infinite series in the next video. All right, thank you for watching, and I'll see you in the next one.